All right, so let's get started. Today we're back talking about diffusion models. I think there is still a few things that we didn't get a chance to cover. So specifically, we're going to see how to think about score-based models as a diffusion model. And so where does the name come from and what's the relationship between denoising, score matching, and other kinds of training objectives you might have seen before. We'll see how we can think of a diffusion model or even a score-based model to some extent as a type of variational autoencoder at the end of the day, a hierarchical one, but essentially a variational autoencoder, and there's going to be some connection between evidence lower bounds and the denoising score matching losses that we've been seeing. Then we'll go back to kind of like interpreting diffusion models as normalizing flows. This is the sort of idea of converting an SDE to an ODE that we briefly talked about, but we didn't have time to go into a lot of detail, which will allow us to compute likelihoods exactly because it's a flow model. And then we'll talk about how to make sampling efficient. So take advantage of the fact that once you view generation as solving some kind of ordinary differential equation or stochastic differential equation, then you can use advanced numerical methods to accelerate sampling. And then we'll talk about controllable generation. So if you want to build a text-to-image model or you want to use some kind of control, some kind of side information to, let's say, generate an image, how do you bring that into the equation? How do you change the models to allow you to do that? So let's start with a brief recap of score-based models. Recall the underlying idea there was that we're going to model a probability distribution by working with the score function, which is this gradient of the log density of the log likelihood, essentially, with respect to the input dimensions. So you can think of it as a vector field that basically tells you in which direction you should move if you want to increase the likelihood. And we use a deep neural network to model it, and this score model, which is like a neural network that takes, let's say, an image as an input and maps it to the corresponding score or gradient of the log likelihood evaluated at that point. And we've seen that the score can be estimated from data using score matching kind of losses. And it's kind of like a relatively simple regression-like loss where you try to compare the estimated gradient to the true gradient. And you kind of look at the L2 distance between these two vectors, averaged over the data distribution. And we've seen that there are ways to rewrite that loss into one that you can, at least in principle, compute and optimize as a function of theta. That's intractable, or at least expensive with respect to the data dimension. But we've seen that there is something called denoising score matching, which basically is much more efficient. The kind of basic idea is that instead of trying to estimate the score of the data distribution, you estimate the score of a version of the data distribution that has been perturbed with, let's say, Gaussian noise. So you have some kind of kernel or a noise kernel, which is just like a Gaussian at the end of the day, that will take a sample X and will add the noise to it. And that defines basically a new distribution, Q sigma, which is basically just like what you get by convolving the original data distribution, which is unknown, with some Gaussian kernel. So it's just kind of like a smoothed out version of the data distribution. And it turns out that estimating the score of this Q sigma instead of P data is actually efficient. And there is this kind of, if you look at the usual kind of like regression loss where you compare your model with the true score of the noisy data distribution averaged over the noisy data distribution, turns out that objective can be rewritten into a denoising objective. So basically, if you can train a model S theta that can take a noisy image, X plus noise, and tries to basically estimate the noise vector that was added to the image. So if you can somehow go from this noisy image to the clean image, or equivalently, you can figure out what was the vector of noise that was added to this image, which if you subtract it, will give you back the clean image. So if you can denoise, then you can also estimate the score of the noisy data distribution Q sigma. And this does not involve any kind of trace of the Jacobian. It doesn't involve any sort of differentiation. It's just a straightforward loss that is basically just denoising. The reason we're doing denoising is because by solving the denoising objective that you see here in the third line, you are actually learning the score of the noise perturbed data distribution. And that's a good thing to have access to, because if you have the score, then you can basically use Langevin dynamics to effectively generate samples. So you kind of like, if you know how to denoise, then you know how, in which direction perturbing your image would increase the likelihood most rapidly. So you kind of have like a Taylor approximation of the log likelihood around every data point. And you can use that information to inform the way you produce, you explore displays, and you generate samples. The trade-off is that you're no longer estimating the score of the clean data distribution, but you're estimating the score of the noisy data distribution. And so, yeah, it's much more scalable. It reduces to denoising, but the trade-off is you're not estimating the score of the data distribution. You're estimating the score of the noise-perturbed data distribution. And then, yeah, once you have the score, back to the question, once, if you somehow are able to estimate the scores, then you can generate samples by basically doing some kind of noisy, stochastic, kind of a gradient ascent procedure, where you just initialize your particle somewhere, and then you follow the arrows, essentially adding a little bit of noise at every step, trying to move towards high probability regions. And we've seen that in order to make this work, it actually makes sense to not only estimate the score of the data distribution perturbed with a single noise intensity, but you actually want to estimate the score of multiple versions of the data distributions that have basically where each version has been perturbed with a different amount of noise. And so you have kind of like these different views of the data distribution that have been perturbed with increasingly small, in this case, amounts of noise. And what you do is you train a single model, a single score network, which is conditional on the noise level. So it takes a sigma as an input, and it will estimate the score for all these different data distributions perturbed with different amounts of noise. And if you can train this model, then you can do basically Langevin dynamics, where what you would do is you would initialize, if you have this good model of the score, then you would initialize, which you estimate it by denoising score matching. What you would do is you would then do Langevin dynamics, where you would initialize your particles somehow, then you follow the gradients corresponding to the data distribution perturbed with large amounts of noise. You reduce, you improve the quality of your samples a little bit, and then you use these samples to initialize a new Langevin dynamics chain for where you're going to use the scores of the data distribution perturbed with a smaller amount of noise. And again, you follow these gradients a little bit, and then once again, you take these particles and you initialize a new chain for an even smaller amount of noise, and you keep doing that until you have the sigma is small enough that basically you're sampling from something very close to the true data distribution. And this is a new Langevin dynamics, and you can see here how it would work. So you would start with pure noise, and then you would run this sequence of Langevin dynamics chains, and you would eventually generate something that is pretty close to a clean sample. So you can see that it has this denoising flavor, where you would start with pure noise, and then you slowly remove noise until you reveal kind of like a sample at the end. And this is just, again, Langevin dynamics. At every step, you're just following the gradient, more or less, and you go towards a clean data sample at the end. So now that this was all recap, now what we're going to do is we're going to start to think about this process as a variational autoencoder, right? So if you think about it, what's going on here is that we are sort of like going from right to left. If you think about multiple versions of the data distribution that has been perturbed with increasingly large amounts of noise, what we're doing is we're starting with pure noise, and then we are iteratively removing noise by running these Langevin chains. So we run a Langevin chain to kind of like try to transform xt into a sample from the data distribution with a fairly large amount of noise. And then we use these particles to initialize a new chain where we follow the gradients corresponding to a data distribution with a little bit less noise. And then we run it for a little bit, and then we keep going until we kind of like generate a clean sample at the end. So we can think of the procedure that we were seeing before as basically trying to iteratively generate samples from these random variables, x0 through xt, where these random variables are essentially what you would get if you were to take a real data sample and you were to add noise to it, right? Because we were estimating the scores of these noise-perturbed data distributions that were indeed obtained just by taking data and adding noise to it, right? That was the whole idea of the noise conditional score network, right? And so this is essentially at an intuitive level what's going on. We're iteratively reducing the amount of noise that we have in the sample. And so the inverse of this process is the one that we've used to basically train the network to generate samples for the denoising score matching loss. And we can think about the inverse process, which is the one that you would use if you wanted to go from data to pure noise. And that's a very simple process where at every step, you just add a little bit of noise. So if you want to go from x0 to x1, you take a data point and you add a little bit of noise. If you want to go from x1 through x2, you take a sample from x1, you add a little bit more noise. And as you go from left to right, you add more and more noise until at the end, there is no structure left, and you're left with basically pure noise. And so you can start to see that this sort of like has the flavor a little bit of a VAE, where there is kind of like an encoder process, and then there is a decoder process down here. And we'll make that more formal, but that's sort of like the intuition. And so the more specifically, basically what's going on here is that there is a relatively simple procedure that we're using to generate these random variables, x1, x2, all the way through xt. And that procedure is just adding noise. So at every step, what you do is if you have a sample from xt and you want to generate a sample from xt plus 1, what you do is you take xt and you add noise to it, just Gaussian noise. So that defines a set of conditional densities, q of xt given xt minus 1, which are just Gaussians, where these Gaussians have basically a given mean and a given variance, and the mean is just like the current sample, xt minus 1, rescaled. It's not super important that there is a rescaling there, but the way you would generate a sample xt given a sample xt minus 1 is you would draw a sample from a Gaussian with a mean, which is just xt minus 1 rescaled, and some fixed standard deviation or fixed covariance. And so we can think of this process of going from data to noise as some kind of like Markov process where at every step we add a little bit of noise. And perhaps we rescale by some fixed constant beta t. Not super important that you do the rescaling, but that's how it's usually done. And so I'm having it here just to make it consistent with the literature. And this basically defines a joint distribution. So given an initial data point x0, there is a joint distribution over all these random variables, x1, x2, all the way through xt, which is just the product of all these conditionals, which are just Gaussians. So that sort of like defines a joint. Given an initial data point x0, there is a joint distribution over all these other random variables, x1 through xt, where the joint is given by a product of conditionals. So it's kind of like an autoregressive model, but a little bit more simple because it's Markovian. So the distribution of xt does not depend on all the previous ones, but it basically only depends on xt minus 1, on the previous time step. And I'm using the notation Q because it will turn out that this is indeed like the encoder in a variational autoencoder. So you can think of this process of taking x0 and mapping it through this vector of random variables, x1 through xt, as some kind of encoder. And the encoder happens to be pretty simple because all you have to do is you just have to add noise to the original data point x0. So in a typical VAE, what you would do is you would take x0 and then you would maybe map it through some neural network that would give you a mean and a standard deviation for the distribution over the latents. Here, the way we get a distribution over the latents, which in this case are just x1 through xt, is through this procedure. So there is nothing learned. You just add noise to the original sample x0. So this defines some valid procedure of basically defining multiple views of an original data point x0, where every view is kind of like a version of the data point with different amounts of noise. The output, technically for this encoder, is higher dimensional than x0 in the sense that it's the whole collection of random variables. Each one of the random variables, xt, has the same dimension as x0. It's t times the dimension of the original data point. And yes, the mapping is not invertible. We're adding noise at every step. So that defines some way of basically mapping a data point to some latent variables or a vector of latent variables through this very simple kind of like procedure where you just add noise to it. And it turns out that adding Gaussian noise is pretty convenient because you can also compute, because everything is basically Gaussian, so the marginals of this distribution are also Gaussian. And so if you want to compute what is the probability of observing a certain like noisy view of a data point x0 after t steps, that's another Gaussian, where the parameters of that Gaussian basically depend on these beta coefficients that we had before. Again, not super important how you take the betas and you combine them to get the alphas. What's important is that if you add a little bit of Gaussian noise at every step, the result of applying this kernel multiple times is also another Gaussian, with just different mean and a different standard deviation, but you can basically compute them in closed form. So the probability of transitioning from x0 to xt is some other Gaussian distribution, where the parameters of this Gaussian basically depend on the effects of each of the individual transitions that you would do to get through to time xt. And this is important for a couple of reasons. First of all, basically it's efficient to simulate this chain. So if you want to generate a sample at time step t, you don't have to generate the whole process of going through t steps. You can directly kind of like sample from this marginal distribution without having to simulate the whole chain. And yeah, if you choose the parameters in the right way, this is essentially the same exact way we were generating training data for our denoising score matching procedure. Remember, in the denoising score matching procedure, what we were doing is we were taking clean data and we were adding different amounts of noise corresponding to different time steps or different noise levels, sigma, generating all these different views, kind of like of the original data, corresponding to different amounts of noise levels. And so it still achieves the same kind of like effect, but we're thinking of it as a process that adds noise incrementally at every step of this process, which you can also think of it as a diffusion process, right? You can think of what's going on here as a diffusion process where there is an initial distribution over data points, which is the data distribution, which could be, for example, like a mixture of two Gaussians. It kind of looks like this. Here, the colors basically indicate the intensity of how large the PDF is at that point. So yellow points tend to have higher probability mass than, let's say, these blue points that are more closer to the tails of these two Gaussians. And what's going on is that we're basically defining these noise perturbed data distributions by basically adding noise. So we randomly draw a sample from the data distribution and we add noise to it. And by doing that, we define all these noise perturbed distributions where, as you can see, kind of like the shape of this distribution changes as you add more and more noise. You see that there is no probability mass here in the middle, but if you add a little bit of noise to the original samples, then you're going to get a little bit of probability mass here in the middle. And then if you add a lot of noise, then basically everything just becomes Gaussian. And so you can think of it as a diffusion where basically given an initial condition, this, which is just a data point on this line, then you can imagine simulating this, this process where you add noise at every step, and eventually the probability mass is going to be all spread out, sort of like all over the space. And this kind of like behaves like the process of heat diffusing, let's say in a solid or some sort. And so that's why it's called a diffusion, because there is some kind of process that takes probability mass and then diffuses it over the whole space. And this process of essentially is defined by the transition kernel, which is just basically the Gaussian. In theory, yeah, all you need, like if you think of it as a, well, maybe we'll come back to this in a few slides, but yes, to some extent, you need several things. You need to be able to smooth out, kind of like destroy the structure, so that you end up with a distribution at the end that is easy to sample from. Because essentially what we're going to do at inference time is we're going to try to invert this process, and we're going to try to go from noise to data. So first you have to define a process that destroys structure and goes from data to noise. And the noise that you get at the end has to be something simple. It has to be efficient, so you need to be able to kind of like simulate any slice here efficiently, because we'll see that the learning objective will end up being denoising score matching, and so you need to be able to sample from it efficiently if you want to use denoising score matching like objectives. Other than that, pretty much, yes, you get a valid probabilistic model. If you have those two things, then you can essentially use this machine. And it turns out that the way to invert this process exactly involves the score. So if you have the score, then you can invert the process. Or if you think of it from a VAE perspective, as we'll see, then you can also just try to basically invert the process by trying to learn some kind of like decoder that will try to invert. You can think of this process of going from data to noise as an encoder. Then you can try to just training an elbow just by variationally try to learn an operator that goes in the opposite direction, which might not involve the score in general, but if everything is Gaussian, then it turns out that, yeah, what you need is the score. The important thing is that the original data distribution here, okay, it's a mixture of Gaussians, but it can be anything. It doesn't have to be remotely close to a Gaussian distribution. It has to be continuous for this machinery to be applicable directly, although we'll see later when we talk about latent diffusion models that you can actually also like embed discrete kind of data into a continuous space, and then it will all fall out pretty naturally from a VAE perspective. But the initial distribution doesn't have to be Gaussian. It could be just a distribution over natural images, which is far from Gaussian. What's important is that the transition kernel that you use to spread out the probability mass is Gaussian, so that kind of like you destroy structure in a controllable way. And you know that after adding a sufficiently large amount of Gaussian noise, you have a Gaussian distribution. The signal to noise is basically extremely low, and at that point, sampling from a pure noise is the same as kind of like starting from a data point and adding a huge amount of noise, essentially. This is just, okay, this is a diffusion, and that basically maps from data on the left-hand side here to pure noise on the right-hand side. And what this suggests is that there might be a way of generating samples which basically involves the process of inverting this procedure. So we had a simple procedure that goes from data to noise just by adding Gaussian noise at every step. So we had a collection of random variables with some well-defined joint distribution, which was just like that Gaussian defined in terms of the Q that, you know, given an xt minus 1, you define the next one by just adding noise to it. If we could try to generate samples by inverting this process. And so what we could do is we could try by initially sampling a value for this random variable x capital T. And we know that x capital T comes from some known distribution. For example, it's just pure Gaussian noise. And this notation here, this pi, you can think of it as a prior, some fixed distribution that this diffusion process basically converges to. So that's easy. And then what we could try to do is we could try to basically reverse this process by sampling from these conditionals. So you would sample xt minus 1 given x capital T, and then we could go back and one step at a time and going from pure noise to data. And this procedure would work perfectly if somehow we had a way of knowing what this distribution is. So we know how to define q of xt given xt minus 1, because that's just a Gaussian, but the reverse kernel, which goes from xt to xt minus 1, the one that goes from right to left, is actually unknown. And that's sort of like why this procedure cannot be directly used, but what we can try to do is we can try to learn some kind of like approximation of this reverse kernel that goes from kind of like right to left, that basically learns how to, so that we can learn basically how to remove noise from a sample. And so basically that's the core underlying idea. We're going to define, now you can start to see it, we're going to define a decoder or an iterative decoder, which has the flavor of a VAE. You start by sampling a latent variable from a simple prior, which could be just a Gaussian distribution. And then we go from right to left by sampling from these conditionals, p of xt minus 1 given xt, which are defined variationally in the sense that these are sort of like, this is our generative model. This is how we usually, just like in a VAE, the decoder is defined through some sort of neural network. In this case, the probability density over xt minus 1 given xt is a Gaussian. And as usual, the parameters of the Gaussian are computed by some neural network. So it's the same sort of like flavor of a VAE, where you would sample z from a simple prior, and you feed z into some neural network, like the mu theta here, to get a parameter for a Gaussian distribution over x, and then you would sample from that distribution. It has the similar flavor here in the sense that the reverse process is defined variationally through these conditionals, which are parameterized in terms of neural networks. And so there is a true denoising distribution that would map you from xt through xt minus 1. We don't know what this object is. We're going to approximate it with some Gaussian, where the parameters of the Gaussian are learned, as usual, like in a variational approximation. And we're going to try to choose theta so that these two distributions are close to each other intuitively. So that what we get by sampling from this variational approximation of the reverse process is close to what we would get if you were to sample from the true denoising distribution. And so more specifically, this basically defines a joint distribution, which is going to be our generative distribution, where we basically first, which essentially just corresponds to that sampling procedure that I just described, where there is a prior distribution over the rightmost variable, this xt, which we know comes from a simple distribution like a Gaussian. And then you would sample from all the remaining variables one at a time, going from right to left by sampling from these conditionals, which are all Gaussian with parameters defined by through some neural networks. The key thing here is that we choose the parameters. So we choose this alpha t such that basically there is no signal to noise at the end. And so you are basically left with pure noise. So basically this alpha bar t goes to 0 essentially by choosing basically, you might imagine that if you add a sufficiently large amount of noise, it doesn't matter where you started from, everything kind of like looks the same. And so that's sort of like the trick. You have to define a diffusion process such that, and you have to run it for a sufficiently long amount of time, which is kind of like the same thing, such that sort of like you forget about the initial condition, or you eventually reach a steady state where, which is known. It's some sort of like Gaussian distribution with some known sort of like mean and standard deviation, so that you can sample from it at the end. Yeah. And so that's what's going on here. There is a distribution Qt, which is going to be close indeed to some Gaussian, for example, which you can always set it up if you choose the transition kernels in the right way. As we'll see, you can actually do something similar by using Langevin dynamics. So because it turned out that if you train this thing variationally, this mu that you learn is basically the score. And so as we'll see, there is basically one way of generating samples, which basically just involves t steps, where you just do step, 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 t times until you get clean, you get a good, somewhat, whatever, hopefully a good approximation of a clean data point, but you don't really know. It only depends on how well you've learned this reverse process. If you're willing to throw more compute at it, you can actually do more compute at every step to try to invert the process better. One way to do it is to do Langevin dynamics. So Langevin dynamics is just a general way of generating samples. It's like an MCMC procedure to generate samples from a distribution. At the end of the day, we know what kind of distribution we're trying to sample from here, which is just like the noisy data distribution. And if you had the score of that distribution, and you can generate samples from it. And so we'll see that there is a way to kind of like correct the mistakes that you would do if you just were to use this vanilla procedure by putting in more compute. Like if you wanted to sample from this joint, what you would do is you would sample xt, then you would sample xt minus 1, xt minus 2, all the way through x0. There is no Langevin dynamics at this point. So there is not deterministic, it's stochastic, because this transition is a Gaussian. So you would have to sample from a Gaussian where the parameters are given by some neural network. So the neural network part would be deterministic, but then just like in a VAE decoder, it's stochastic. The mapping is stochastic. Okay, so now we've defined two things. We basically have an encoder and we have a decoder essentially here, which is parameterized by these neural networks mu theta. What we can do is, and so we can kind of start viewing this as a hierarchical kind of like VAE or just a VAE, where there is an encoder that takes x0, a data point, and maps it stochastically to a sequence of latent variables, which are just like the x1, x2, x3, all the way through xt. And there is some kind of like prior distribution over the latents, which is just this p of xt, this is just simple Gaussian. And then there is a decoder that would basically invert the process. And the decoder is, in this case, as usual, just parameterized using neural networks, which are going to be learned. So just like in a VAE, there is an encoder and a decoder. So it has kind of like the flavor of a VAE, except that kind of like the latent variables, there is a sequence of latent variables that are indexed by time, and they have this specific structure where the encoder is actually fixed. There is nothing learned about the encoder. The encoder is just adding noise to the data. So it's kind of like a VAE where the encoder is fixed. So a very special kind of structure. So recall that the vanilla VAE would look something like this. You have a latent variable model, you have a latent variable z, which has a simple prior distribution like a Gaussian, and then there is a decoder which would take z, map it through a couple of neural networks, mu and sigma, and then p of x given z is defined as a kind of simple distribution, a Gaussian, where the parameters are given by these two neural networks. And then you have the encoder, which does the opposite. It takes x and it basically tries to predict z. And again, that's usually some simple Gaussian distribution where the parameters are usually computed by some other neural network that takes x as an input and gives you the parameters of the distribution over the latents. And we know that you would train this model by maximizing an elbow, an evidence lower bound that would look something like this. So you would basically guess the values of the latent variables using the encoder. Then you have the joint distribution over observed variables and latent variables as inferred by the encoder. And then you have this term that is basically just encouraging high entropy in the encoder. So this is the vanilla version. What we have here is kind of like a hierarchical version of the vanilla VAE. So if you were to replace this single latent variable z with two latent variables, you will get something that looks like this, where the generative process would start by sampling z2 from a simple prior, and then passing it through a first decoder to generate z1, and then another decoder to generate x. And so you have a joint distribution, which is just the product of all this, the prior over z2, the first encoder and the second encoder, and then the second decoder, sorry. And then you have an encoder, which is what you would use to infer the latent variables given x. So it's a distribution over z1 and z2 given x. And you would have an evidence lower bound that would look like this, just like before. Here we have a simple prior over z. If you replace this with a VAE, then you get what we have here. And so that would be the training objective. And so that is exactly what we have in the diffusion model. So in the diffusion model, well, we don't have just two. We have a sequence of latent variables, but it's essentially the same thing. We have a joint decoding distribution, which is what you get by going from right to left. And then we have an encoder, which is fixed, which is just adding Gaussian noise to the images. The way you would train this model is by minimizing some elbow loss or maximizing the elbow, average it over the data distribution. And so just like before, the objective function would look something like this. So here Q of x0 is just the data distribution. And so you would want to maximize the true log likelihood over the data distribution, and we don't have access to it, so instead you use the evidence lower bound, which is just like the usual thing, Q of z given x, P of x comma z divided by Q of z given x. That's the usual evidence lower bound. And there is just a minus sign because I want to minimize that objective as a function of theta. And what would you plug in? So Q is fixed. Q is just this product of Gaussians, which is this process of adding noise at every step. And P theta is the interesting bit, is this distribution that you get by starting from some simple prior, like pure Gaussian noise, and then kind of passing it through this sequence of neural networks that will try to kind of like infer the parameters of some other Gaussian that you sample from to go through this sampling procedure. So that's how this joint in the numerator is defined. It's defined in terms of this P theta of xt minus 1 given xt. And so it's just like, you could try, you can optimize this loss as a function of theta. And so it's actually a little bit simpler than the usual VAE. In the usual VAE, Q itself is learnable. Remember, you have those 5 parameters. Here Q is fixed, so you don't have to actually optimize it. So it's kind of, it's just like a VAE, except that the encoder is fixed. It's not learnable. That's the usual elbow objective. And recall that these decoders are parameterized, are all Gaussians, and they have this simple form, where to sample xt minus 1, you would take xt, you pass it through some neural network to get the mean, and then they will have fixed kind of like variance. And the interesting thing is that if you parameterize these neural networks, they'll give you the means of these Gaussians using this form, which is, again, it depends on these betas and these alphas, not super important, but kind of like if you parameterize the network in terms of an epsilon network that takes xt as an input and then tries to predict the noise that was added to xt and subtracts it from subtracts this estimated noise from xt, to get a guess of what xt minus 1 should be, then you can show that this elbow objective is actually equivalent to the usual denoising score matching loss. So minimizing the negative elbow or maximizing the lower bound on the average log likelihood is actually the same as trying to estimate the scores of these noise-perturbed data distributions. And so if you were to, basically, if you parameterize these mean networks by saying, okay, take the data point that you have and subtract something to make it look more realistic, and this network essentially ends up trying to estimate the score of these noise-perturbed data distributions. And so, although we derived everything from the perspective of a variational autoencoder, it turns out that what you're actually doing is estimating scores. So the score-based model would sample differently. So here I'm just claiming that the loss would be the same as up to some, I guess there is some scalings, but roughly, if you look at it, you're basically starting from data, you're sampling a noise vector, you're feeding the noisy image to this network epsilon, and you're trying to estimate the noise vector that was added to the data. And so the training objective, if you choose this kind of parameterization, are the same. Then you have different choices in terms of how you sample from it. Like in a score-based model, you would sample by doing Langevin. Here, you're not sampling using Langevin. You would sample based on just going through the decoding process. Right? So this is the training procedure of DDPM, of the denoising diffusion probabilistic model. And if you look at the loss is basically denoising score matching. Like if you look at the loss that you have here, that's the same as the denoising score matching loss that we had before. The sampling is also very similar, actually, to what you would do in a score-based model. If you look at the way you would generate samples, is you start from pure noise, same as score-based models, and then at every step, you basically follow the gradient, which is epsilon theta, and add a little bit of noise, because that's what you're supposed to do if you were to sample from a Gaussian that is p of xt given, or xt minus 1 given xt. And so the sampling procedure that you get by iteratively sampling from these denoisers actually is very similar to the Langevin dynamics. It's just different scalings, basically, of the amount of. This is kind of like follow the gradient, take a step in the gradient direction, and then add noise. You basically just do different amounts of noise, essentially. But it's roughly the same procedure. Usually, you would learn the encoder and the decoder together, and they would try to help each other out in some sense. The encoder is trying to find structure, and the decoder is trying to leverage the structure to generate data more efficiently. Here, the encoder is fixed, and it's just adding noise. And so the decoder is just trying its best, basically, at minimizing the KL divergences that you would have, or basically maximizing the elbow, which is the same as inverting the generative process. And turns out that in order to do that, you need to estimate the scores. And to the extent that you can do that process well, then you would be able to generate good samples. It seems like you would have an easier time by actually allowing yourself to learn the encoder as well. But that doesn't actually work in practice. So it would give you better elbows, but worse kind of like sample quality. You can also do one step of Langevin. In practice, that's what you would do. And so at that point, I mean, what's the difference? I mean, they're essentially the same thing. I think one advantage of the score-based model perspective is that you can actually think of it as like in the limit of infinite number of noise levels, as we'll see, which is not something it would be a little bit trickier to get with the VAE perspective. But to some extent, they're essentially the same thing. I mean, from the elbow perspective, you're going to get better numbers if you learn the encoder. But then, I don't know if it's an optimization issue, but then in terms of like the sample quality, you're going to get blurry samples, kind of like in the sort of like in a VAE. Well, there's some intuition related to progressive coding, and in practice, people don't actually optimize the elbow. In practice, people optimize a scaled version of the elbow. So the elbow, do I have it? Yeah, so the elbow basically looks like this, where you have these lambda t's that basically control how much you care about the different type steps. And in the limit of infinite capacity, it doesn't matter. But then in practice, people would set them to be all one. So, which is not the same, which is not what you should do if you wanted to optimize the elbow. So it's the matter of optimizing likelihood. It doesn't necessarily correlate with sample quality. So even if the encoder is fixed and it's just something really simple like outing Gaussian noise, the reverse is not, it requires you to have the score. So it's non-trivial to actually invert it. But you could argue that maybe if you were to destroy the structure in a more structured way, then maybe it would be even easier to invert the generative process. Yeah, so they generalize to some extent, not out of distribution. So if you train it on images of cats, they're not going to generate images of dogs because they've never seen them, and there's no point for them to put probability mass on those kind of. So it's really based on the actual data distribution that you have access, that you're using for training the model. So when you add a lot of noise, the best way to denoise is to basically predict the average image in the data set. And so there you already see that if you've trained it on images of cats, what the network will do when t is equal to capital T, it will basically output the average image in the training set. And so it's going to be completely off. I think one of the main reasons is that if you think about it, the amount of compute that you can put at generation time is very large because you're going to kind of like pass it through kind of like 1,000 VAEs essentially. Maybe T is usually, capital T here is 1,000 usually. So it's a very deep stack of VAEs that you can use at generation time. However, because of how things are set up, at training time, you never have to actually look at this whole very deep, very expensive computation graph. You can kind of like train it kind of like layer by layer, incrementally, without actually having to look at the whole process. So even though you just train it locally to just get a little bit better at every step, which is very efficient. It's all breaking down, yeah, over kind of like levelable level. Yeah. So the stack of VAEs would exactly give you this. Like the problem is that if the encoders are not structured in a certain way, you might not be able to do this trick of basically jumping forward. Remember that we had this, now it's back a lot. This process here, it's very easy to go from x0 through xt. If these queues are arbitrary neural network, there is no way for you to jump from x0 through xt in one step. And so the fact that these queues are very simple and you can kind of compose them in closed form allows you to get a very efficient training process. So not all hierarchical VAEs would be very efficient to train, but this is a particular type of hierarchical VAE, so there are certainly some that would be efficient. If you were to just train the VAE the usual way, you would get a loss. If you go through the math, it ends up being the same thing. It seems counterintuitive that you would want to fix the encoder to be something strange like this, where you kind of like just add noise and you're not reducing the dimensionality. But once you start making that choice, then the loss ends up being the same as the denoising score matching loss. Historically, we came up with the score matching first and showing that it works, and then people show, okay, you can take a VAE and you can get something essentially identical, and that saves you a little bit of trouble at inference time because you no longer have to do Langevin dynamics, you can just sample from a VAE. So the lambda basically is just something that turns out to be kind of like how much you care about the different denoising losses over different noise intensities. And there is a principle, like if you just do the math and you go through the elbow, there's going to be certain value of lambda t that you should choose if you really cared about the evidence lower bound. In practice, people just choose that to be 1. And so you're not actually optimizing an elbow. beta is the parameters, beta t's. The alphas are computed in terms of the beta t's. That basically controls how quickly you add noise to the data, essentially. And you can choose it. So at the inference time, we do start from random noise and then move it back to the sort of like clean data. But it kind of like makes sense to do it incrementally, as opposed, you could also do it in one step. Like you could imagine a VAE where the encoder is fixed, takes the image and adds a lot of noise. Presumably that inverse distribution that you would have to learn, which is this, where do I have it? This procedure here that tries to invert the process, going from noise to data, is going to be very complicated. While if sort of like Q of xt given xt minus 1 is kind of like the same thing, just adding a little bit of noise, presumably inverting that is also going to be relatively easy. And so we're kind of like breaking down this complicated problem, going from noise to data, into 1,000 little sub-problems where all you have to do is to just remove a little bit of noise. And that ends up being better in practice because the sub-problems are much more tractable to learn. So what you do is you start with a data point, you randomly pick a t, which is like an index in this sequence of noisy random variables. Then you start with just a standard Gaussian noise, and then you generate an xt by basically adding the right amount of noise. So it's the same as kind of like denoising score matching. So this argument that you feed into epsilon theta is just a sample from Q of xt given x0. Yeah, so the architecture is the same as a noise conditional score model. So you have the same problem that you need to learn a bunch of decoders, one for every t, and instead of learning 1,000 different decoders, you learn one that is kind of like amortized across the different t's. So you have the same, like this epsilon theta network that is trying to predict noise. Basically it takes the image, xt, the noisy image, it takes t, which is encoded somehow, and those are both inputs to the network that then are used to predict the noise. So that's the same as the noise conditional score network where you take xt, you take sigma or t, and then you use it to predict the noise. And so yeah, the architecture would basically be usually some kind of UNet, because we're sort of like doing some kind of like dense image prediction task where we go from image to image, and UNet type architectures tend to be pretty good at this, and this is still, I mean, people are using transformers too, but this is still one of the best performing models for learning a denoise. So we have a paper that you can look up on trying to get a hierarchical VAE to perform, because the one problem with the hierarchical VAE is that basically there is a lot of, if you start learning the encoder, it's not identifiable. There's many different ways to, you basically want to encode the information about the input across all these latent variables. But there's many different ways to do it. Like which bits of information you store where in the latent variables is very much up to the encoder and the decoder to figure out. It turns out that if you use a certain kind of encoding strategy that is kind of like forcing the model to spread out the bits in a certain way, then you can get pretty close to the performance of, with a learned encoder, you can get pretty close to the performance of these kind of models. But yeah, it's still not entirely clear how to do it. There are multiple papers on trying to figure out good noise schedules. There's many different choices. What's important is that at the end, the only real constraint is that at the end, you basically, the signal to noise ratio is 0 essentially. So you destroy all the information. Then there is a lot of flexibility in terms of like how much noise you add at different steps, such that it will get you at that result. You can even try to optimize it. If you take the elbow perspective, you could just maybe learn a simple function that kind of like controls how much noise you add at different steps. So you still just add a Gaussian noise, but you can try to learn how to. So there are ways to even learn the schedule. I would go in the direction of maybe let's learn the encoder, or let's make it more flexible. In practice, I mean, there are a number of papers where people have tried different strategies, different ways of destroying structure called diffusion. They've shown some empirical success, but in practice, people still mostly use Gaussians. What we can do now is start thinking about what happens. We have this diffusion model perspective, hierarchical VAE kind of perspective, where we have clean data, and then we have 1,000, let's say, different versions of the data distribution perturbed with increasingly large kind of like amounts of noise. Really, if you think about it in terms of a diffusion process is a continuous time kind of process. If you think about how heat diffuses over some metal bar, that process is not happening at discrete time intervals. It's really more naturally thought as something happening over continuous time, where time is continuous. And so, or another way to think about it is you can imagine making this discretization finer and finer. Maybe you find we're still going to take the hierarchical VAE perspective, but you can start thinking about what happens if we were to take more and more steps. If we go from 1,000, 2,000, 4,000, we make these steps smaller and smaller and smaller and smaller until eventually we kind of like get this continuum of distributions, which really correspond to the diffusion process. And so we have as usual, on the left-hand side, we have the clean data distribution, which is this mixture of two Gaussians, where there's kind of like these two spots where most of the probability mass is. And then there is this continuous time diffusion process happening here that is spreading out the probability mass over time until at the end, on the right-hand side, you get this pure noise kind of distribution. So literally what's happening here is just we're thinking about a very, very, very fine-grained kind of discretization or a lot of different steps over which we go from data to pure noise. So if you were to destroy the structure a very little bit at a time, you can imagine in the limit, you get a process that is continuous. And so instead of having 1,000 different distributions, we have an infinite number of distributions that are now indexed by t, where t is now like a time variable going from 0 to capital T, just like before. But instead of taking 1,000 discrete different values, it takes an infinite number of values. So it's a continuous variable going from 0 to capital T. And so we have, as usual, data on the one hand, and then pure noise on the other extreme. And so how do we now describe the relationship between all these random variables that are now indexed by time? We can describe it in terms of a stochastic process. So there is basically a collection of random variables, and there is an infinite number of random variables now. In the VAE case, we had 1,000 different random variables. Now we have an infinite number of random variables, xt. And all these random variables have densities that, again, are indexed by time. And instead of describing their relationship using these encoders, we can describe how they are related to each other through a stochastic differential equation, which is basically the way you would describe how the values of these random variables that are now indexed by a continuous time variable t are related to each other. And so what you're saying is that over a small time interval dt, x changes by an amount which is determined by some deterministic drift and some small amount of noise that you basically add at every step. Not super important what that formula means, but without loss of generality, you can think about a very simple kind of like stochastic differential equation that describes a diffusion process where all that's happening is that over a small time increment dt, what you do is you change the value of x by adding an infinitesimally small amount of noise, essentially. And that is basically how you describe the encoder, or how all these random variables are related to each other through this essentially diffusion process. Now, what's interesting is that, just like before, we can think about the reverse process of going from noise to data. And the random variables are the same. We're not changing them. But it turns out that they can be described equivalently through a different stochastic differential equation that now goes, where time goes from large to small, from capital T to 0. And what's interesting is that this stochastic differential equation can be, has a closed form solution. And again, not super important what the formula is, but the only thing that you need to know to be able to characterize the stochastic differential equation is the score function. So just like in the discrete case, in the VAE case, kind of like if you knew the score, then you would get optimal decoders and you would be able to reverse the generation process. In continuous time, if you have all the score functions, you can reverse the generative process and go from pure noise to data. Yeah, so it's closed form up to the score function, which is unknown. So maybe a little bit of a, but there is a, basically this is the equation. This exactly inverts the original stochastic differential equation if you know the score function, which you don't. So you're right that we don't know it, but if you knew it, then you would be able to exactly invert the process. So the stochasticity is basically this dWt. Basically, at every infinitesimal step, you add a little bit of noise, and in the reverse process, you're also doing it. So in that sense, it's a stochastic differential equation. So if that term was 0, so if you didn't have that here, then it would be an ordinary differential equation, where the evolution is deterministic. So given the initial condition, like if this GT here was 0, or this piece doesn't exist, then you would have just a regular ordinary differential equation. Given the initial condition, you can kind of integrate it, and you would get a solution. This one is a little bit more complicated because at every step you add a little bit of noise. And so that's why you kind of have these paths here that are a little bit, see all these little jags that in the curve? That's because there is a little bit of noise that is added at every step. If you want to do things in continuous time, what we can do is we can try to learn a model of all these score functions, which is just like before, is going to be a neural network. It takes as input x and t and tries to estimate the score of the noise perturbed data density at time t evaluated at x. So this is just like the continuous time version of what we had before. Before we were doing this for 1,000 different t's. Now we do it for every t between 0 and capital T, where t can be is a real valued variable. We estimate it again doing score matching, denoising score matching. So it's the usual thing where we estimate scores of the noise perturbed data density. We can do denoising score matching, and the solution to that regression problem is basically a denoising kind of objective. And then what we can do is to sample, instead of using the decoders and go through 1,000 steps of the decoders, we can actually just try to solve numerically the reverse time stochastic differential equation, where we plug in our estimate of the score for the true score function. So here we had the exact stochastic differential equation. Okay, sorry, this doesn't show right, but let's see whether, yeah. So we had this differential equation, which involves the true score. And now we are approximating that with our score model. And then what we can do is we can try to, in practice, we cannot solve this in continuous time. In practice, you will still have to discretize it by taking small steps. And there are numerical solvers that you can use to solve a stochastic differential equation, and they all have the same flavor of basically you update your x by following the score and then adding a little bit of noise at every step. If you were to take 1,000 different steps, and you would essentially do that kind of machinery of sort of like using the decoders, that basically corresponds to a particular way of solving this stochastic differential equation, which is just this kind of discretization, Euler-Maruyama kind of discretization. What a score-based model would do instead is it would kind of like attempt to kind of like correct, because there are numerical errors, you're going to make some mistakes. And so what a score-based model would do is it would try to basically fix the mistakes by running Langevins for that time step. So you can kind of like combine just regular sampling from a diffusion model where you would take 1,000 different steps or even less with MCMC style sampling to kind of like correct the mistakes of a basic sort of like numerical SDE solver. It's not normally distributed. So it's a normally distributed conditioned on the initial condition. But the marginals are far from normal. The transitions are, yes, that's key. Yeah, because then that's why we can simulate it forward very efficiently. But marginally, they are not. DDPM is just this. It's like a particular type of discretization of the underlying SDE. Score-based models would attempt to solve this SDE in a slightly different way. That there is basically two types of solvers: predictor solvers, corrector solvers. Basically, score-based models, which is MCMC or Langevin dynamics, is something called like a corrector method for SDE solving. So it's just a different way of solving the same underlying stochastic differential equation. So DDPM is just predictor. Score-based models is just corrector. You can combine them and just get a more accurate solver for the underlying SDE. DDIM is a different beast. DDIM works by basically converting let me skip this, but basically converts the SDE into an ODE. So I guess we're out of time, but again, it turns out that it's possible to define an ordinary differential equation that has the same marginals at every t as the original stochastic differential equation that we started from. So now the evolution is entirely deterministic. There is no noise added at every step. So you see that how these white trajectories, they are very kind of, there is no noise added at every step. They're kind of straight. But marginally, they define exactly the same densities. So the probability that you see across time are the same. Whether you run this kind of simple diffusion, kind of Brownian motion kind of thing, or you do this deterministic, you follow these deterministic paths, the marginals that you see, like how frequently do you see this trajectory is going through different parts of the space, are exactly the same. So there are two advantages. One advantage, and again, it still depends on the score function. One advantage is that, as you said, you can be more efficient. The other advantage is that now it's a deterministic invertible mapping. So now it's a flow model. So now we've converted a VAE into a flow model. Basically, what's happening is that, if you recall, you can think of these random variables here as latent variables in some kind of generative model. And in the VAE perspective, we're inferring these latent variables by stochastically simulating this diffusion process. But if you solve the ODE, now you're inferring the latent variables deterministically. And because ODEs have unique solutions, the mapping is invertible. And so you can also convert basically this model. Once you have the score, you can convert it into a flow model that has exactly the same kind of like marginal densities over time. And one advantage of a flow model is now you can compute likelihoods exactly. So now you can use something similar to the change of variable formula to actually compute exactly what is the probability of landing at any particular point. You can just solve the ODE, which is the same as kind of like inverting the flow, and then compute the probability under the prior, and then you do change of variable formula, and you can get exact likelihoods. And so by converting a VAE into a flow, you also get exact likelihood evaluation.